Have you ever wondered why, for decades, making neural networks really deep was almost impossible? Researchers would add more layers, expecting better performance, but their networks would simply stop learning. The reason for this failure has a name: the vanishing gradient problem. It is a fundamental challenge that we had to overcome to get the powerful models we have today. To understand the problem, let us quickly recap how a network learns using a process called backpropagation. After the network makes a prediction, backpropagation sends an error signal backwards through the network. This gradient tells us how to adjust each weight. A large gradient means make a big change. The vanishing gradient problem is exactly what it sounds like. The error signal gets weaker and weaker. The weights in these early layers barely update at all. They are effectively frozen. The culprit is the chain rule. To find the gradient of an early layer, you multiply the gradients of all the layers after it. A key part of that calculation involves the derivative of the activation function, like the sigmoid function. For most inputs, the derivative is much smaller, a number between 0 and 1. What happens when you multiply many numbers that are less than 1 together? They vanish towards 0. This chain of multiplications crushes the gradient until it is useless. This problem is especially severe in recurrent neural networks, or RNNs. When we backpropagate through an RNN, we are repeatedly multiplying terms related to the network's weights. This means the network cannot learn long-range dependencies. It forgets the main subject of the sentence. The machine learning community came up with several ingenious solutions to this roadblock. First, we switched activation functions like the rectified linear unit, or ReLU. ReLU has a derivative of either 0 or 1, so it does not squash the gradient to a tiny value. Residual networks introduced a brilliant idea: the skip connection. The gradient can flow backwards through this identity connection, giving it a direct path to the early layers. For RNNs, a new architecture called long short-term memory was designed to fight vanishing gradients. LSTMs have internal gates that control what information is remembered, forgotten, and passed along. Smarter ways of initializing weights and methods like batch normalization also help keep gradients in a healthy range. The vanishing gradient problem is a consequence of the chain rule. It crippled deep learning for years. But through clever architectural changes and smarter training techniques, we found ways to protect the gradient. If you want to learn more about the building blocks of modern AI, be sure to subscribe to blackboardAI. Let us know in the comments what topic you would like to see broken down next. Thanks for watching.